Let's demonstrate a wave plate with our polarization lamp. So remember, this has a nice illuminated front surface, but it has two crossed polarizers in front of it, one with a transmission axis one way, one the other way. And remember, if I put a polarizer in between, that lets some light leak out. Remember, this was a mind-blowing experience. If I take a wave plate, it's going to convert linear light to some elliptical state, and that also lets it out. So here you can see if I hold it at 45 degrees, I'm taking the polarized light, I'm putting a little bit along the fast and the slow axis. It's creating some elliptical form of the light and letting it out. But if I turn it, it doesn't let the light out anymore, right? Because if the polarized light is along one of the fast or the slow axis, it doesn't have the effect of altering the polarization state. So there you get nothing, 45 degrees, good, there you get nothing again. So pretty boring. It acts just like the polarizer. You might even think maybe it is just a polarizer, but I promise you it's a wave plate. And you can actually tell because the polarizer knocks out half the light. That's why it looks kind of tinted, whereas the wave plate lets through all the light because all it's doing is changing the polarization state. Also, if I look for glare with the wave plate, I can't see glare. It's not a polarizer, even though it acts like one here. So wave plate is sort of a horrible way to demonstrate this because it's so uninteresting. Here's something very interesting. This is cling wrap or saran wrap or food wrap or plastic wrap or whatever you call that plastic stuff you have in your kitchen to keep food fresh. So if you take a little bit of this and just sort of bundle it up a little bit and stick it in here, then you see these interesting colors show up. Bundle it a little differently like that. There you go. So you see some interesting effects, some colors show up, and you see different domains where the thing has been cut in different layers. So there's quite a bit of interesting wave plate-like effects going on in here. So if we can understand that, I think we understand birefringence and wave plates quite well. So let's do plastic wrap between crossed polarizers. Okay, and let's see if we can describe it with Jones vectors. So to start, the light has to go first through that first polarizer. And we're going to think about the polarizers as being at 45 degrees. Okay? Because we want to think of the wave plate as being vertical. Don't worry about the details for now. So the light will go through the first polarizer, and that'll get it polarized at 45 degrees. And then it's going to hit the wave plate, which is really the wrap. And for now, let's just pretend the wrap is a wave plate or a phase retarder with its slow axis vertical like that. Really, it's all mushed up plastic. We'll get to that part later. But basically, it's got its axis like this. So the phase that you end up with is d over lambda naught 2 pi times delta n, just like we talked about before. Okay? And then it's going to go through another polarizer, and it's got its TA that way. And then the question is, what comes out? Okay? So linear light, this does some kind of elliptical polarization. Who knows what comes out of here, and then what comes out of there. So if the wrap isn't there, you get nothing out. That's why the lamp is black, is this polarizes it this way, this is at 90 degrees, nothing comes out. But the wrap lets light through. So let's do our Jones treatment of this situation. We're going to start here, because we don't like to deal with unpolarized light. So this gave us light right here, and if we wanted to write it as a normalized Jones vector, it would be 1, 1, 1 over square root of 2. Okay? So if we took the magnitude of that, it would be 1/2, or 1 over square root of 2 squared plus 1/2. 1/2 plus 1/2 is 1. Right? So that's a normalized vector for that light right there. The first thing it hits is the wrap. So for the wrap, we need that generalized phase retarder, which, well, if we're going to say the general for vertical SA, that was 100 e to the j phi. Right, so this is the phase lag it applies to the vertical light, because the SA is vertical. Right? And then it's going to go through the other polarizer. So if this created it at 1, 1, this way, this must be the polarizer half, 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 half. So the one The other way is half, negative half, negative half, half. So this would be negative 45 degrees, and therefore the, the signs make these two terms negative. Okay? So those are the matrices we need to multiply to see what, if anything, is going to come out and what it looks like. Okay, so let's pull the 1 over square root of 2 out to the front. Let's hold on to the half, 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 half. All right, so first the light has to hit this. So this is going to be 1 over e to the j phi. Yep. Okay, that's the light. And now we multiply our cross polarizer by the light, and we get 1 over the square root of 2 times something more complicated than what we've seen before. Half minus 1/2 e to the j phi. So this is not a 2 by 2 matrix, it's a 1 by 2 matrix. So this is one entry, and then minus 1/2 plus 1/2 e to the j phi. And that is the light that comes out. So if you see something this complicated, you think this is some sort of elliptical light. It's not just a simple linear or circular RCP, LCP. It's something more complicated. So we just got to start simplifying it to see if we can figure out what happens. One thing you could do is pull out a half, right? So this could be 1 over 2 times the square root of 2, and it's 1 minus e to the j phi over minus 1 plus e to the j phi. Okay, that looks a little nicer. It's still not linear or RCP or LCP or anything, but let's just keep going, and the next step would be to find how much light gets out. Is this 0? What's it going to be? Let's make sure that some light is going to get out. Okay, well, we multiply each one of these by its complex conjugate and then add the two things together. So what I'll do is first keep this amplitude separate to make it easier. So this times itself is an eighth, right? 2 times 2 is 4 times 2 is 8. So we're going to say 1/8 out here. And then this times its complex conjugate plus this times this complex conjugate. So that's 1 minus e to the j phi times 1 minus e to the minus j phi plus minus 1 plus e to the j phi times minus 1 plus e to the minus j phi. That would be the irradiance. All right, so 1/8. And let's see, that's going to be 1 minus e to the j phi minus e to the minus j phi. That doesn't really help you much. Let's just write all the terms. And then minus times minus is plus, and then e to the j phi to the minus j phi is e to the 0 is 1, so plus 1. And then here we have minus 1 times minus 1 plus 1, and then minus e to the j phi minus e to the minus j phi, and then this final term is 1 times e to the 0, which is 1. All right, there's all the terms. So what does this simplify down to? Is it going to go to 0? No, it's not going to go to 0. It's going to be 4. E to the j phi's are both negative, minus 2 e to the j phi. E to the minus j phi's are both negative, minus 2 e to the minus j phi. Okay, well, we can pull out a 2, and the 2 cancels the 1/8, so it's 1/4 2 minus e to the j phi minus e to the minus j phi. Let's see. Did we give up there? No. Now let's go ahead and make it real. Okay, so that's going to be equal to 1/4 of 2 minus, and e to the j phi is cosine phi plus j sine phi, right? So it's minus cosine phi, and then minus j sine phi. That's right. And then it's minus cosine minus phi minus j sine minus phi. Okay, cosine and sine, one is symmetric, one is not, right? Cosine is symmetric. The cosine of minus x equals the cosine of x. So whenever you see a cosine of minus something, you can just ditch the minus sign, right? Cosine of phi, cosine of minus phi, same thing. So for the cosine, I just erase the minus sign and leave that minus sign there. For the sine of minus phi, it's equal to the minus sine of phi, right? So it's asymmetric. So when you erase that, you got to put that there, and you put that there, and that cancels that. There we go. So this becomes 2 minus 2 cosine phi. All right, let's see if we can finish here. That equals, pull out the 2, and you get 1/2, 1 minus cosine phi. And the imaginary part went away, as it should. The whole point of taking that complex conjugate to get the amplitude is it should be something real. Okay. Let's see, what is that? That's saying that our amplitude, our radiance, is proportional to 1/2, 1 minus cosine. But what was phi in the first place? Phi was 2 pi d over lambda naught times delta n. 2 pi d over lambda naught times delta n. That's the irradiance. And this sort of explains why the plastic wrap is so interesting looking, because we shove it in there and we have different layers and they have different thicknesses. So how much light you get out depends on the thickness. So that's why when you see a boundary, it's a very sharp boundary between one layer and two layers. It's because it's either one thickness or two thicknesses. And it's colorful because the wavelength matters. Right? How much light gets through depends on how many cycles it goes through. As it's in the material, how many cycles it goes through depends on the wavelength. So different colors will end up coming out either crossed with a polarizer or along the polarizer or circular to the polarizer. It depends on the wavelength. So that's why you get this sort of complex behavior when you stick saran wrap between two polarizers. You're still not convinced? Okay. This is a complicated mess. Let me take this out, and I made you something a little bit more controlled. I put individual layers of plastic wrap onto a glass slide. So first let's establish one thing. Glass is highly isotropic. So there is no birefringence in glass. Here's a glass slide, and as I turn it around, it doesn't let any of the light through. You get a little bit at the edges, but that's light reflecting off the edges of the glass. So you can see the glass isn't going to do much. So glass is a good substrate to put in plastic wrap. So now I have a single layer of plastic wrap on this slide. And if we put it in, you can see it lets the light through, kind of a light blue color. If I turn it, no more light gets through. If I turn it this way, no more light gets through. It's acting just like a wave plate. Because it turns out the direction for the SA and the FA of plastic wrap has related to the way they make it. So it actually does go along the rolls. So here I cut it in a way that it really is right along that axis. Okay, it's just a single layer of plastic wrap. So you can see that part seems to be true. And here is 2 layers of plastic wrap, and they sort of overlap in the middle. So there you can see kind of the grayish bluish of a single layer, and there's 2 layers, kind of a golden yellow, right? And then here, this will show you 3 layers of plastic wrap. See, goes from the kind of this color, the grayish, and then kind of the gold yellow, and then kind of a red, kind of a brown, right? There's 3 layers. What does 4 layers look like? Oh, okay, now kind of a very bright blue part shows up in the middle. So you can see it definitely is due to the different numbers of layers of plastic wrap. And it is a birefringence effect. You can see as I turn it there, it definitely changes. Let's see if it makes any sense mathematically to further convince you. So let's think about plastic wrap here. So now we're going to fill in some numbers and see where we are. Equals 1/2 1 minus the cosine. And let's think about what's inside this cosine. We have a 2 pi And D is the thickness of the birefringent material. Plastic wrap is about 10 microns thick. So that's about 10 to the minus 5 meters. Right? And the wavelength of light in the visible is about a half a micron. So what is that? That's 5 times 10 to the minus 7 meters. So 500 nanometers would be 5 times 10 to the minus 7 meters. And the anisotropy, basically the difference between N in one direction and N in another direction for a typical sort of stretched plastic like this is about 0.04. It varies, obviously, it depends on a lot of things, but I'll put about 0.04. And what you can see from this is if we multiply it out, we're not too far from basically 0, or not 0, but around the order of 1. Right? Because say if this 5 cancels that 5, that 4, say that becomes like 1. This is 10 to the minus 2. 10 to the minus 2 times 10 to the minus 5 is 10 to the minus 7. It cancels that 10 to the minus 7. So we're on the order of 2 pi radians. And that's important. That means if we're near the order of one cycle, rather than being at 10,000 cycles or being at negative or being at a billionth of a cycle, the fact that we're around 1 cycle means when you change one of these, you'll get a big effect on the cosine. It means we're in the part where the cosine does this, not where it goes like this, or where it goes like that. Because this comes out around unity for sort of visible wavelengths is why we get these colors. And I'll even prove that to you. So here are some plots assuming an anisotropy of 0.04 and a thickness of 10 to the minus 5. And I do them for all the wavelengths in the visible. Here is for cross-polarizers, and for having your stuff at about 45 degrees, your plastic wrap at 45 degrees, this is the spectrum you would get. This is the irradiance that would come through, basically the transmission. And you can see through the visible, it's pretty much half the light gets through here, and almost all the light gets through here at the red. So that's why one layer is kind of gray. Okay? 2 layers, then you actually get a minimum down here in the red, and you get a lot in the blue. So 2 layers becomes more colorful than 1 layer, and that's what we saw. 3 layers, you get another peak here in the visible and a dip in the visible, more colors but a different color. 4 layers, more colorful. And you can see what's happening is the more layers you add, there's 5 layers, the larger D is. You're increasing D, therefore you're increasing the frequency in this sinusoid. Right? That's why this looks like a cosine or a sinusoid that's getting higher frequency, and it's mixing in more and more colors. If you put a huge number of layers, the effect would eventually be washed out, and it would be gray again. If you put a very thin layer, the effect is washed out and it's gray again. Okay? You only get the colors when your phase ends up sort of around a single phase. And for plastic wrap, it just happens to occur when you have a few layers of 10 micron thick plastic wrap at visible wavelengths with an anisotropy of around 0.04. It just happens to happily work out that way. You're still not convinced? All right, how about if we measure it? All right, here, cross polarizers, and here's an optical fiber going to a spectrometer that'll let us take the spectrum of the light going through the stuff, the plastic wrap, and we'll see if it looks like what I calculated. So here is our 5-layer plastic wrap sandwich on glass, and now I'm going to put this up to the gray 1 layer, and you can see not much variation over the visible wavelengths that you're seeing there. So then I'll come up to 2 layers right here, and you can see it's different. Not a lot of structure in the visible, but it's definitely a different curve, right? Then I'll go to 3 layers, and curve changes again. That's why it's a different color. And go to 4 layers. Oh, the curve changed quite a bit. And now you can start to see kind of the sinusoidal character of the curve. And 5 layers, and more kind of sinusoidal look to the curve. So you'll notice in my calculation, it got quite a few oscillations in the visible. And here, it's going a lot slower. The reason is probably I overestimated the anisotropy. When I said the difference between the N vertical and N horizontal is 0.04, it's probably too big. It's probably more like 0.02 or 0.01. But one way we can kind of deal with that is if I stack all the plates. Now we have layers as much as 13. And if I stick it in between the 2, there's all of our pretty colors. And now let's hit a few of these and see if we get more of a sinusoidal character, more higher frequency inside the spectrum. And sure enough, there you can see when I hit different layers, it jumps around now with multiple peaks inside the transmittance curve. So that's why you see colors when you have cling wrap, or I'm sorry, plastic wrap between cross polarizers.